I'm Ben Shaw, and this is Youngwoo Chang, and we're studying chemical engineering at the University of Kansas.
So you, like most people, might be wondering, what the heck is chemical engineering? And quite frankly, we're not very sure about that either. Why don't we go ask a few people? Let's go. Okay, so what's your name and what's your major?
My name is Sarah, and my major is behavioral neuroscience.
Yeah, my name's Thomas, and I'm majoring in microbiology.
My name is Ryan. My major is communication studies.
I'm Olivia, and my major is biology.
Well, my name is Dr. Susan Williams. I'm the chair of the Chemical and Petroleum Engineering Department at KU.
All right, and what do you know about chemical engineering?
Not much. My roommate was chemical engineering, but I don't really know what she was doing with that.
Not a lot, just like it's tied into like petroleum and like the oil industry, I think.
Pretty much that it's the foundation of our society.
Yep, not a lot.
So chemical engineering is a really awesome profession where students get the opportunity to combine their knowledge and love of chemistry, math, physics, biology, the fundamental sciences and math, and put those together to really convert raw materials into more valuable and useful products. And I tend to be pretty biased, but usually I'll tell students if you think of a product or you think of a process that you might be interested in, I can tell you where chemical engineering fits into the process.
You know, I couldn't have said it better myself, Dr. W.
Now let's take a look at one company where chemical engineers work. Have you ever gone in for lunch at your favorite restaurant, touched the door handle, and then the chair that hundreds of other people have touched the same day, and then started eating your food without even thinking about washing your hands?
Have you ever come home from a rough day at school, throwing the same backpack you set down in various classrooms, and probably even bathrooms on your bed? Think about how many germs are spread in that moment.
Now that's what Mark Sisson and Dennis Hackemeyer were thinking when they created nanoseptic technologies. Let's take a close look as to how these technologies work. So nanoseptic technologies. Basically, they're self-cleaning surfaces. But how do they clean themselves? Turns out, nanoseptic uses a unique self-cleaning mechanism called photocatalysis. Now nanoseptic uses a main ingredient called titanium dioxide, which when it comes into contact with sunlight, creates free radicals or unstable atoms. And when these unstable atoms come into contact with germs, viruses, or any foul organic matter, it breaks them down. And now you might be wondering, are the particles still left on there? You're right, but that's where the next step comes in, which is the superhydrophilicity of titanium dioxide, which allows, instead of water traveling in beads across the surface, it allows the water to travel as a film, which means a wider surface area is cleaned off and washed off in the end.
By now, hopefully you're convinced that this nanoseptic stuff is legit. Let's talk about the more important stuff. Money. When you go on their website, it shows they're in 4 main markets: commercial cleaning and faculty management, hospitality and travel, healthcare, and education. But really, those aren't the markets they're in. Those are the main customer categories, as they provide products to hotels, airports, hospitals, schools, and various other businesses. Their real market is hygiene. The hygiene industry is valued at $34 billion, and the hygiene company giants are SC Johnson, 3M, Clorox, and Purell, all of which nanoseptic beat out to win an ISSA Innovation Award in 2016. Be that as it may, the hygiene industry as a whole is a little too large. Nanoseptic is more accurately put into the self-cleaning industry, which is valued at $3.3 billion. Here, they compete with self-cleaning paint, glass, and coating makers such as Sherwin-Williams and Pilkington.
Nanoseptic self-cleaning surfaces can be used in virtually any high-traffic points, which would accumulate bacteria over time. Now these include door handles, airport baskets, restaurant menus, and public mouse pads.
Why don't we see how much they cost? At first glance, the prices are very low and affordable even for a college student at more or less than $5 per product. When you look a little closer though, it doesn't look quite as good. Still reasonable, just not incredible. First, it is recommended that nanoseptic surfaces are replaced every 2 to 3 months. Ultimately though, it depends on the physical wear on the surface, not an expiration. So a door handle with heavy traffic may need to get replaced monthly, while a personal mouse pad may last a couple years. Secondly, most customers would probably want to buy in bulk and not an individual surface because most buildings have more than one door, believe it or not.
So now we know how nanoseptic works, where it's found, and how much it costs. But where does chemical engineering actually come into play? Now, apart from the R&D done in the new lab facility, it turns out that most chemical engineers work in the titanium dioxide plants, where raw ilmenite ore is turned into usable titanium dioxide, the active ingredient in nanoseptic. Now this process is done through acid leaching, which can be broken down into 3 separate chemical reactions: dissolution, extraction, and precipitation. Now in dissolution, what happens is raw ilmenite ore is added to sulfuric acid, where a solution of sulfates is created, including titanyl sulfate. And then in extraction, the titanyl sulfate is hydrolyzed to create hydrated insoluble titanium dioxide. And then with that, we go into precipitation, where in a calciner, the solid collected is then heated up to dry out the titanium dioxide to create usable titanium dioxide. While all of this goes on, regeneration also occurs from the acid used in extraction and dissolution. Now because of this regeneration, this process can have a continuous flow rather than a batch production. Now from the waste produced from the extraction process, which includes iron and other hazardous chemicals, waste management is also a large part of this process.
So what do chemical engineers do in the process?
Chemical engineers would work in the manufacturing process of the self-cleaning surfaces themselves. But since this is such a newly developing field, it is difficult for us to gather information as to what this manufacturing process actually looks like. But we do know the roles they play in the extraction of titanium dioxide. For example, they would work in the process and control engineering side of things, where they would oversee the efficiency of acid leaching and calcination. Or they would work in chemical reaction engineering, where they would oversee the reaction and regeneration of the acid. And finally, in waste management, involving the chemical byproducts. Some useful skills for a chemical engineer in this field to have is a strong background in chemistry, and specifically in redox reactions, and biochemistry, as it involves human interactions with these self-cleaning surfaces. And other professions that are involved in this field are researchers in biochemistry, organic chemistry, or biology, ilmenite ore miners to mine the ilmenite ore used to extract titanium dioxide, mechanical engineers to aid in controlling the process, and finally environmental engineers to assess the impact around cities and around the globe. We think this nanoseptic chemical engineering stuff is pretty cool. We hope you do too.
Thank you for watching, and don't forget to smash that like button.